All right, this is going to be AP Calculus Lesson 5-8. We're talking about piecewise integration. Where are we in the unit? We are on 5-8. We are after this lesson, we are one lesson away from finishing the unit. So let's go ahead and do the setup. Go ahead and pause me. All right, now that you've unpaused me. So we're trying to find this integral from 0 to 4 of this function, and f of x is defined by this piecewise function, x plus 1 if x is less than 2, and 3 if x is greater than or equal to 2. So I want to solve this graphically first, and then after that we're going to solve it with only an equation, no more graphs. So let's look at what this looks like as a graph. X plus 1. Let's go ahead and make a line here. X plus 1, maybe I should make only a line with no arrow. X plus 1 from this interval here, it goes to 2, and it has a slope of up 1 over 1. So right 1, up 1, and then after I hit 2, all of a sudden it changes the function. This would normally continue on forever and ever, and I can maybe show that with a dashed line. Actually, I think that would be confusing. We'll just say, yeah, it could continue up and up, but it stops. At 2, it changes to the constant function of 3. So 3 is just this constant flat line here, and that ends at 4. Okay, so now that we have that set up, let's go ahead and do what we did in our homework last night, where we find the area under this curve. So between the x-axis and the function, so I'm going to make that line here. Whoa. And what area am I trying to find? We'll shade that in now. So I'm trying to find this area right here. And it's going to be positive. It's above the x-axis. And now let's break this up to make it a little bit easier. So if I come right, okay, well, it should have been at 2. I'm going to kind of fudge this a little bit and do a slightly diagonal line. And we'll divide this up like this. We can say that this is going to be a little rectangle here. All right, so what are our areas? This is a 2 by 1, so it's an area of 2. This is going to be a 2 by 2. That's 4. Half of 4 is 2. And this is going to be a 2 by 3, which is an area of 6. So our final answer here is going to be, wait, what's going on here? Yeah, it's going to be 6 plus 2 plus 2, and that's going to be 10. We got 10 using the graphical method. Perfect. So we can say, yay, we found that. That's equal to 10. Yay. How do we do this without a graph now? How do we go fast? Because sometimes these are going to be really hard, and I just want to do the integration with pure equations. So to do that, we want to find the area of two curves, essentially. So we know that f of x, this f of x, is two functions. If there's two functions, I'm going to need two integrals. I'm going to do one integral for this function and one integral for this function. What is that going to look like? So if I come down here, and I'm going to have an integral, and I know it's going to be between 0 and 4. So from 0 to 2, I guess this was 0. From 0 to 2, it was this function. So I'll say from 0 to 2, and notice what 2 is. 2 is called, do you remember the name of this guy? This 2 here is called the suspect point. Suspect point. The suspect point is going to usually be the break. It'll go from 0 to the suspect point, and then from the suspect point to the end. 0 to suspect point to the 4. All right, so I have my function 0 to 2, and this function is x plus 1. So I'll say x plus 1, all of that d of x. And we need to add that with another integral from, again, the suspect point to the end, 2 to 4. I'm just saying from 2 to 4. And of this function here, this function was 3 d of x. All right. So now I need to evaluate these individually and calculate their areas. So this integral, and I'll do it down below here. If I do x plus 1 and I integrate, this is going to be x squared. Divide down, it's going to be 1/2 plus x. That's going to be evaluated with our evaluation bar between 0 and 2. And set up our right-hand side. So this is 3, so it's going to turn into a 3x when I integrate, and that's going to be evaluated between 2 and 4. All right, so let's do that now. So this is going to turn into, I think I might need to work on the right here. Actually, that might be confusing. I'm going to work underneath because we'll see that this goes to this. All right, so subbing in 2. 2 squared is 4, half of that is 2, and then 2 plus 2 is 4. So I have a 4 minus, and subbing in 0, I get a 0. I'm going to add this with our function over here. Subbing in 4, 3 times 4 is 12. Subbing in 2, 2 times 3 is 6. Notice what's happening here. This area here is 4 for this entire integral, and this integral applies to this area here. So these two add up to 4 because this is also 4. I mean, they should match up, right? And then this one is 6, this one is also 6. So this is going to turn into 4 plus 6, which is equal to 10. So we can get the same answer only using integration without graphing. All right, so to summarize, I mean, we're not done. We have one more slide, but we basically have as many lines as there are in the piecewise function. That's how many integrals we'll have. Let's try this with an example. So go ahead and copy this down. All right, you've unpaused me now. So how do we do this? We have two different functions, so we need two integrals, and I will explicitly write that down for us too. So I'm not going to say we're not going to use complete sentences. I was going to write we have, no. So we have two pieces of the piecewise function, which is going to imply we need two integrals. All right. So we're going to take the antiderivative. So step 2, take the antiderivative. Antiderivative. All right. And we need to do that by taking our two pieces. So I'm going to do that down here. So we're taking the antiderivative, the integral from, oh, and I didn't even ask the question yet. I should have written that down in our setup, but I'll do it now. We're trying to find the integral of from 0 to 6 of our function f of x. We'll put dx here too. So I need to go from 0 to our suspect point, so 0 to 2. So my first, okay, switch back to blue because it's no longer the example. So I'm going to go from 0 to the suspect point of the function, and the function for this first part from 0 to 2, when I'm less than 2, I am at 2x plus 4, so 2x plus 4. Don't forget our dx. All right, and I need a second integral. This thing is equal to, by the way, I should have said this, all of this turns into this, 2x plus 4 dx, and from our suspect point from 2 to 6, because I end at 6 here, of our function over here. So this is going to be x dx. Perfect. So we need to take that antiderivative. So here we go. We're taking the antiderivative. And if you would like, we can write down the sub-steps here. So it goes start to suspect point, suspect of the first function. First, what am I doing here? First function. And then usually you'll have two, but you'll go suspect to, I'm going to say end of your end of the second function. All right, so, and from here you're just still doing the antiderivative, and let's see what that looks like. So 2x plus 4, antiderivative of that is going to be a x squared plus 4x. Again, this is going to be x squared dividing down. The 2 divided by 2 leaves a 1, and 4x, because this was 4x to the power of 0, 4x to the power of 1. And that's going to be evaluated between 0 and 2. We need to add this to the antiderivative over here. So this is going to be x squared, and then divide down, so 1/2 x squared, evaluated between 2 and 6. Let's see what that becomes. 2, subbing in, 2 squared is 4, plus 4 times 2, so it's 4 plus 8. 4 plus 8 is 12. 12 minus, subbing in 0, I get 0. Perfect. So that was our first part. And I'm going to add it to this. So let's sub in 6 first. You always start with your endpoint. 6 squared is 36. Half of that is 18. 18 minus, and subbing in 2. 2 squared is 4. Half of that is 2. So I'm really saying 12 plus 16. And that is going to be equal to, I guess I was going to go on the right. I should just go down. This is going to be equal to 28. All right, so the homework has one problem where you do the graphical to make sure you understand what's going on, and then the graphical directly translates into the pure analytic, the pure equations. All right, go ahead and write your summaries.